Okay, so we can start. Today we're going to look at relative velocity. So to start with, what is relative velocity? So relative velocity, whenever you see the word relative, it means that we are comparing usually two things. Relative usually means we are comparing two things. Yeah. So now, in this case, we are saying relative velocity, meaning we'll be comparing two velocities. Yeah. So, in case the screen stops showing, don't worry, the video is still being recorded, so you'll be able to watch it smoothly. So now, I was saying relative velocity is when we compare two different kinds of velocities. So, an example which we can talk about is, let's say we have a car like this. Oh, and by the way, it's been so quiet. Can anyone just confirm that you're able to see the car which I've drawn? So just react to it. You can even unmute yourself and then you say you can see. Are you able to see the screen? Was that something I didn't get you clearly? Yes, Moses, you're able to see?
Yeah, I'm able to hear your voice, but I'm unable to see the screen.
Oh, okay. So, let me just ensure the screen is visible. So, how about now? Are you able to see it?
No, I'm unable to see it.
Okay.
I can't see it.
Okay. Yeah, so since we can see the screen now, I was saying relative velocity is when we compare the velocity of two things. Yeah, so let me give you this example. Let's say we have a car like this. Okay, we have a car, and then in this car, maybe let's say in the back seat, we have two people seated. We have one person and the other person there. So you have to follow me closely here. Relative velocity usually seems to be a challenge for a number of people because of these concepts. So we'll understand it together. So imagine we have a car which is moving. It is going to the right. And then we have two people. So the one who just joined us, is it Grace? You're welcome. This is when we started. So if we have two people in a car, we have one here and the other one is seated there. So now the question would be, this person who is seated here, the person who is seated here, and the person who is seated on the other side, as the car is moving, if you think about it, do you think that, yeah, so how can I put this? So let me just redraw. So we have two people like this. Yeah, so these two people, they are in a car. So these two people are in a car which is moving. So now the idea I'm trying to put across is, when the car is moving to the right, do you think that this person who is seated here, they are both seated in the back seat? When this person looks at the friend, if you think about it very nicely, when this person looks at the friend, will the friend look like the friend is remaining behind? So for that one, I'll answer for you no. So, and then for you to understand this even better, we're now going to put an idea of a tree. So I'm sure when you're in a car, you've seen something like this, whereby when the car is moving, you are going to see a tree. You see a tree quite alright, and then after some time you feel like the tree has remained behind. You feel like the tree has remained behind. So in that case, would we say that the tree is going backwards? So no, the tree is not going backwards. It is the car which is moving forward. But the tree is looking like it is going behind. Catch, it is the car which is going forward. So we're introducing the concept of relative velocity. Yeah, so we have to understand the surface. So when the car, I'm going to move the car now. The car is moving, it's moving all the way up to there. So you can see at this point the tree has remained behind. So it doesn't mean that the tree was moving. It is just the car which was moving forward. So this is the concept of relative velocity. So the tree remained here behind because the car was moving. Yeah, so now what I was trying to ask you here is, what about when this person, so when this person is looking at the tree, it is looking like the tree is going backwards. Yeah, that's how it looks. But what if this person is looking at the friend here? Will the friend look like the friend is also going backwards? So the friend will not remain behind because they are together in the same car. Meaning this person, when he looks at the friend, it will just be like the friend is not moving. Yeah, this is the concept of relative velocity. We look at two things, we compare the velocities of two things. So now we start from this very example. So let's say we're going to, so we're going to move these things somewhere here. So let's say the car is moving with a velocity of 20 meters per second. That is the velocity of the car. So meaning even these two people, meaning even as they are seated, their velocity is 20 meters per second. That's what it means here. When you're in a car which is moving at 20 meters per second, even your velocity is 20 meters per second. No wonder if brakes are applied, if you are not wearing your seat belt, you pass through the window because you are also moving at 20 meters per second. Yeah, so now let's say this car is moving at this speed, 20 meters per second. And then now when we talk of relative velocity, so we write, so if we say what is the velocity of, so we're going to call this one person A, and then the other one we're going to call him person B. So if we say what is the relative velocity of person A with respect to person B, so how we write this, we say velocity of person A. This is the person we're looking at, person A. So the velocity of person A with respect to B. So we write velocity AB. Okay. Wait. Okay. So I thought it's not recording. So this is the velocity of person A with respect to B. So I think my screen is okay. It has come back. So the velocity of person A with respect to B, it means when A looks at B, what is the velocity? So we said if you look at your friend who is also in the car, it's like the other person is not moving. So in such a case we say 0 meters per second because they are together. It will be like this person is not moving, the velocity is 0. Yeah. So at this point, if you have a question anywhere, you can unmute and then you ask. So if there are any questions. Okay, so I will proceed, but feel free, if you have questions later on, you can always go ahead. So person A, when he looks at B, it is like B is not moving. Okay, so I've understood that point. So now, what about when, what is the velocity of person A when person A looks at the tree? So I'm going to say A relative to the tree. What is the velocity? So here the tree, we can say, we usually use the letter E to say F. So the tree is just on the earth. It is not moving. So now in this case, the tree is, it looks like the tree is going backwards, although it is not really going backwards. So what is happening here? This is why you have to follow it nicely. Since the car was moving forward with a velocity of 20 meters per second, it means that when this person is looking at the other tree, it looks like the tree is also going at a very fast speed, like the tree is also going backwards. So the velocity of the tree, when this person is looking at the tree, the velocity is just the same velocity here, but it will have a negative to show that the tree was in the opposite direction. We say negative 20 meters per second. So this doesn't really mean that the tree was moving at negative 20. It means that when the person is looking at the tree is also going backwards, like at a rate of 20 meters per second. Yeah, so this you understand it very well. If you have a lot of trees, when the car is moving very fast, it will be like also the trees are going behind very fast. Yeah, so I remember when I was young, I used to ask my dad on a bus, like, how come the trees are going backwards? And he laughed at me. So finally I've understood the physics. So when A is looking at the tree is moving with a speed of negative 20 meters per second. Yeah, so since there are no questions at this point, let me also ask you now, what is the velocity of person B when person B observes the tree? So this is B relative to the tree. Anyone to give it a try? So when you try, you won't forget. So what do you think can be the answer?
For me, what I think is, since person A and B, when they're looking at each other, the velocity is 0 meters per second. So I think the velocity is just going to be the same when the person B is also looking at the tree. It's going to be negative 20 meters per second because the tree is still going to be in the opposite direction. That's what I think I right.
Yeah, okay. That's excellent. So just like he has said, person B, when he looks at the tree, it's also negative 20 meters per second. Yeah, because also B is also in the car which is moving. Yeah, so now we're going to introduce the next concept which will take us now to more practice examples. So now let's say we have another car this time around. We have another car. Now we have another car here, and then in the car we have person C. So this one is a VIP. He didn't want to get on a public taxi. He booked a Yango. So this is person C. We're going to call person C Aston, because Aston is the one who just answered previously. So now this car is moving in the same direction. It is moving at a speed of let me put 5. So meaning it is quite slow, 5 meters per second. So now the question is, when so this car, you already understand at this point, this car, it will like overtake because it is moving at a very faster speed. Yeah, so it's going to overtake. So let's even make it overtake. So it's refusing to overtake. Okay, to overtake later. So now the concept I want you to understand at this point now, we're now going to compare person A with person C, and then we observe what happens to the velocity. So remember, relative velocity, we just compare two velocities. So the question would be, what is the velocity of the relative velocity of A with respect to C? Meaning, when A is looking at C, what is the velocity? So now, at this point, what is happening is that this car is moving at a very faster speed, 20 meters per second, but this one is at 5 meters per second. So already it means that this public transport is going to overtake the friend. We've been having a challenge with overtaking. So for those who have cars and they're watching this video, ensure you don't overtake anyhow. So now, the relative velocity of A with respect to C, meaning, okay, yeah, so when A is looking at C, what is the velocity? So at this point, we just get to add the velocities. So we're going to say the relative velocity here, we have 20 meters like that. So this is our 20 meters, and then since this one it's looking like it's going backwards, so what you know is you already understand that the car is moving forward. The car is moving all the way forward, but when this person is looking at this car, it doesn't look like it's moving forward. So when person A looks at the car, it looks like the car is moving backwards. So now what we do is we say 20 minus 5. So the velocity of C is 5. For A it is 20. So 20 minus 5, it's 15. So at this point, what this means, it means that when person A is looking at person C, it's looking like person C is just moving at 15 meters per second. Is this correct? Wait. Okay, so though this is the basic idea, so this car is moving at a slower pace. So this car, the first one is 20, it's moving very fast, but for this one which is moving slower, it's like it is reducing by 15, it's going backwards. Yeah, so now let me give another scenario so that we understand it in another way. So let's say, what is the velocity of C with respect to A? So here it means that when person C, this one is looking at person A, what is the velocity? So this car, it's really moving at 20 meters per second. So in this case, I would say 20. So the velocity for C is 5, and then we add it plus, since this one it is moving all the way forward, we would add it to 20. So we can put 25. Yeah, so this is just the basic idea. So we might have to revisit it later. I'm not sure about something. Yeah, so this is the concept of relative velocity. So now we're going to quickly run through some examples so that we even get to appreciate more concepts. So our first example is this one. We have a train which is moving at a speed of 15 meters per second relative to the earth. Okay, and then there's a passenger standing at the rear of the train. He throws a ball with a speed of 15 meters per second. Okay, relative to the train, and it is in the opposite direction. Yeah, so the statement is quite boring, so we have to start analyzing it. Now, what does this whole thing mean? So in physics, always attempt to draw free body diagrams. Yeah, so depending on the lecture I'm marking you, these can actually be marks. Yeah, so this is our train. Yeah, so let's just imagine that to be our train. So the situation here, the train is traveling at a speed of 15 meters per second. So the velocity of the train relative to the earth meaning the ground. So the velocity of the train relative to the earth is 15 meters per second. Okay, we have gotten that. And then now we also have the velocity of the baseball. The velocity of the ball, like that, relative to the train. So the velocity of the baseball relative to the train is also 15 meters per second. And then they gave us an important detail. It was moving in the opposite direction. So here the train is going this side. Its velocity is 15 meters per second. But the ball is thrown, let's just imagine it's here, is thrown in the opposite direction. So they are both at 15 meters per second. So now in this case, the question now, what is the velocity of the baseball? So what is the velocity of the ball relative to the earth? Yeah, so comparing it to the ground. So for this one, it would require much of our imagination. So here, in simple terms, a train is moving forward and then a ball is thrown backwards. So if you were to watch a movie in such a scenario, since the speeds are the same, so like first let me just calculate. So what we do is we say we'll add the first velocity, this one. Let's get this one, the velocity of the train. So you can even write the formula, though not so important. So these are just for you to so that you do not confuse. So velocity of the train relative to the earth plus the velocity of the ball comparing it to the train. So in case you don't understand what this means, I'll explain it very slow. So I'll start with this one. The velocity of the train relative to the earth. It means that when someone is standing on the earth, meaning someone is just standing down, they're able to see the train. It is moving at 15 meters per second. This is someone who is just standing on the ground. They are seeing, oh, the train is moving at 15 meters per second. Okay, that's good. So the velocity of the train relative to the earth. And I have written VTE. Okay. And then this other velocity now here, velocity of BT. So it means the velocity of the ball comparing it to the train. So this is the ball comparing it to the train. So it is just like we have two people. one is here and then the other one is also here. But in this case now, this person has started moving, so there would be some velocity. Yeah, so this is what these mean. So velocity of the train and velocity of the ball. So we're going to add velocity of the train is 15. So here they gave us a very important detail. It was moving in the opposite direction, meaning, so we say plus. It means that this other velocity is a negative because it was going in the opposite direction. No wonder we say negative. So 15, we say minus 15. The reason I've put a minus 15 for this one is because it was thrown in the opposite direction. If it was also going in that direction, we could have said plus. And then the final answer is 0 meters per second. So this is the velocity of the ball relative to the earth. So for this one, you can actually solve it without calculating. So to understand the concept, it means when someone is standing on the earth and then the train is moving forward by 15, the ball is also moving backwards by 15. It will look like the ball is not really moving. Yeah, it will just look like the ball is stationary. Yeah, so this is on this part. So before we proceed, let me check if there are any questions. So is anyone having a question at this point? Okay, so it seems like we are good to go. So relative velocity, it just takes understanding and a lot of practice. So just practice a lot and you'll be very good. Yeah, this one you don't understand it like maybe in one sitting. You have to go through over and over. But I hope I'm opening up ideas to you. So now, what is the velocity of the baseball relative to the earth if it is now thrown in the opposite direction? Okay. So this question now, question B, it is just the same question. They're saying the velocity of the ball relative to the earth. But in this case now, it is thrown in the opposite direction. So you see this train, the ball is now thrown this side. The ball is thrown this side. So when someone is on the earth, meaning ground, so BE, ball and earth. When someone is on the earth, on the ground, and then they see a ball is moving forward, it will look like the ball is moving at a very fast speed because we have two velocities. The train is moving and also the ball is moving. Yeah. So in such a case, if the train even puts on brakes, the ball will go very speed. Yeah, so let me just explain this point. So we can give an example, like in this train, if there are two people.
Hello, sir.
Yes?
Hello, sir.
Yeah, you can
Yes,
go
I
ahead.
was able to see question. How you answered question 1. So I'm asking if you can repeat.
Oh, okay.
I was unable to see the screen, so I'm asking if you can repeat on question A. How you solved it.
Oh, okay, I've heard you.
Okay.
Okay, so he's asking if we can rapidly go through question A again. So there's no problem. So let us quickly go through question A. What is the relative velocity of the ball relative to the earth? Let me wrap this. So what is the velocity of the ball comparing it to the earth? So meaning when someone is on the earth, when someone is standing here, So this ball was thrown in the opposite direction. So what is the velocity? So what we said is the train is moving forward, meaning velocity is 15. Yeah, they gave us 15. The train is moving forward, velocity is 15. And then the ball was thrown in the opposite direction. So of this ball, it was thrown in the opposite direction. And the velocity is also 15. But since it's in the opposite direction, we're going to give it a negative. No wonder we have a negative here. So what we do, we just simply say, so this is velocity of relative velocity of the ball comparing it to the earth. So we just add the 2. So for this one, this person is trying to observe what is happening. So what you can understand here is that this person is seeing 2 speeds. He's able to see this speed because the train is moving, and he's also able to see this other speed because the ball is moving as well. So this person is seeing 2 speeds. Okay, so since he's seeing 2 speeds, so the simplest way I can say, you just add the 2 speeds. So we say the velocity for the train plus the velocity for the ball. Now which we wrote this, the velocity of the ball relative to the train. Yeah, so we just add the 2. We just say 15 plus the velocity for the ball, we have said it's negative 15 because it was going in the opposite direction. And then I even gave a hint. I gave a hint that if it was going in this way, we could have added, but it is going in the opposite direction, meaning minus. So when you add 15 plus negative 15, that's 0 meters per second. So Kaunda, are we together on that point? Okay, so
Yes.
okay, so that's how we go through this. So now we are going to question B, where they said now this ball is now thrown in that direction. It is thrown forward. So here the simplest explanation I can give you is that this person is seeing 2 velocities, this one and that one. So we just add. So the velocity of the ball observed by the person on the earth, meaning ground, it is for the train, the velocity is 15 plus for the ball it is 15. So now in this case we are not going to use negative 15 because the ball is moving in the same direction. Yeah, so meaning the final answer is 30 meters per second. So if there are questions at this point, you can feel free to go ahead. Now you can go ahead.
No, let's say the screen.
Sorry,
Okay,
start over. You said, let's say the screen.
I just mentioned the calculations.
Okay.
Yes, the screen is not showing up. Yes.
Oh, you are asking on the calculation here.
Yes. Yes, no, it wasn't showing up. I was just waiting somewhere, not seeing.
Oh, okay.
But I've not seen. It started showing.
Oh, alright. So he wasn't able to see this part. so network is quite bad in campus and across. Yeah, so just to make you feel at home, so we're one big family. So quickly again, within 1 minute, what we simply did is the velocity of the ball relative to the train. We said this person, when he's looking at the train, he's seeing two speeds, the speed of the train and also the speed of the ball. So we just add train plus ball, which gave us 30. Yeah, so I'm going to give you an exercise right now, just to see how you are understanding this concept. Okay, so let's say we have this train, the way it is like this, and then it is moving forward with a speed of 10 meters per second, and then a ball, I'm thinking of a hard question now. There's nothing hard. I'm feeling bad that you are going to answer the question. So the speed is 10 meters per second, and then the ball, okay, I'm now going to give an example of a person. Okay, so I have this person. Let's say the person is walking at a speed of -2. This person is going to the right. Yeah, so this is how satanic questions will be. They just want to confuse you. So anyone to give it a try. I'm giving you 2 minutes to think. So if we have a person standing outside here, what is he able to see about the person who is inside? So let's say this is person A. This is person A, this is person B. So what is the relative velocity of A being observed? So let me do this. So this is person A. I don't know how I can put this. Yeah, so I'm just trying to put across. This person is looking at the train again, and then the person is moving. The train is 10 meters per second, and then inside we have a person moving at -2 meters per second. So have you finished thinking? What do you think is the velocity of the person who is observing outside? Anyone to try? Feel free. You will learn even better. So let me check if anyone wants to try. Okay, so you're still thinking. I'll give you more questions ahead, so we can do it together. So remember, we just add the 2. This person is looking at 2 speeds, so I'm going to say 10, the speed of the train, plus the speed of this person is -2 meters per second. Yeah, so -2, that is what is given. So we just write -2. So meaning the velocity of B observed by person A is 8. Yeah, we've just added the 2. And then lastly, we can think of a situation where this person is moving backwards. Yeah, so if this person is moving backwards, again the velocity is -2. So what we do, we're going to add. So let us add. At this point, the person is moving backwards. So we're going to say 10. This is the speed of the train. 10 plus. So always remember, since the person is now moving in the opposite direction, it means we're going to put a minus. So the person is moving in the opposite direction, we put a minus. So 10 plus minus. So this 2, the value is given to be -2. So in such a case, and then the answer will be 12. So this is positive. 10 plus 2, 12. So I was just playing with figures, just to trick your brain. So normally when someone is just going to the left, that's when it's negative. But in such a case, when they just give you a fixed negative value, solutions can work out like this. So now we're going to proceed. So, and then for those who didn't manage to join the live lesson, you can always screenshot, like I was left on that part. You screenshot and then you inbox me on this line on WhatsApp, and then now we can go through together. So now we have another example with us. So for this one, I just got it from college physics, and then in the test, if they bring something like this or the exam, they can't give a diagram. You have to draw the diagram on your own. Yeah, so I just put this just to show you that, okay, that's the diagram, but you have to come up with it yourself. So we have a boat which is heading due north. Under vectors, we learned that due means straight. So due north, meaning that the boat is going straight northwards. So the boat is going north at a speed of 10 kilometers per hour. Okay, that's the first thing. So the boat is going due north, relative velocity is 10 meters with respect to the water. And then the river has a uniform velocity of 5 kilometers per hour due east. So due east, you know it is this side. And then under vectors part 2, if you are done with the Megaminds document, we said where the first vector ends, that's where another vector starts. So due east, normally it means we draw here, but we have to start from where this one ended. So this is due east. You can draw it here. You know this is the Cartesian plane. Due east is here, but we're putting it where the first vector ended. Someone has texted on WhatsApp. They are not able to join. Okay, so I think it's just network that side. So due east is the velocity of the river, meaning this is the velocity of the water. So it is 5 kilometers. Okay. So they want us to determine the magnitude and direction of the boat's velocity with respect to an observer who is on the river bank, meaning someone is just on the ground. Okay, so we can do our data collection. So always remember, during the exam, always collect your data. You even label it. You say data is pronounced as data. So you collect your data, you even underline very neatly. So the velocity of the, what do we have? Velocity of the boat. So we say VB. This is the velocity of the boat with relative to the water. So the velocity of the boat relative to the water. So this is 10 kilometers and it is due north. And then we also have the velocity of the river. So velocity of the river, which is the water. So the velocity of the water. So they have even told us the water is relative to what? So you know, if you have like a river, this is a river. So under the river we just have the earth, the ground. So if they do not tell you what something is relative to, you can just say it is relative to the earth, which is the ground. So this is the velocity of the water relative to the earth. They have given us it is 5 kilometers per hour due east. Okay, and then now the question is, what is the velocity of the observer? Oh, what is the boat's velocity? The velocity of the boat. So VB with respect to the earth, someone who is just down on the earth, what is their velocity? Okay, so someone is saying this. So in such a case, we're just basically calculating this shift, the total displacement. Yeah, so this is a vector problem, but under relative velocity. So what we do, we'll just use Pythagoras theorem here. Yeah, so this is kind of in 2 dimension, although in another video we're even going to look at a very good question, just one question, which is relative velocity in 2 dimension. So for this person who is observing all this which is happening, what is basically happening here is that we have a boat. So I don't know how to draw a boat. Okay, so let's just imagine this is a boat. So it means that the boat is moving forward at 10 kilometers per hour. But it is not only moving forward, it is also moving back this side due east, because the water is pushing it. No wonder that diagram, it was looking like this. Now where is this? So this is our diagram. So the boat is moving straight. The boat is moving straight forward. But since the river is going due east, this means that the boat will be pushed to the other side. Yeah. So I want to calculate the velocity of the boat relative to the earth, meaning on the ground. How is someone observing it on the ground? I hope I've made you understand what is happening. So for the person driving the boat, he's thinking that, okay, I'm going forward. But someone who is looking at him down is able to see that this person is not only moving forward, he's also moving to the right, because there's a speed of water which is 5. Yeah. So this is quite a Pythagoras. It is not in a straight line. So let's say if the boat was moving 10 this side, we can just say 5 minus 10, because they are linear. Linear meaning they're in the same line. We just say 5 minus 10. But in this case, one is moving in the y-axis, the other one is moving to the left axis. So we just don't add, we say 5 plus 10. Mathematics doesn't allow. So we use the Pythagoras theorem. This is the hypotenuse. So we just say adjacent, which is 10 squared, plus the opposite 5 squared, and then you get 11.2 as your final answer. So 11.2 kilometers per hour. Don't forget the units. So for those whom were together, do you have any questions at this point? Feel free. Seems like we can proceed. Okay, so this is the velocity of the boat relative to the earth, 11.2. And then from here, we can also calculate the direction. Now, what would you think is the direction? So, like I said, this is more of a vector problem. So, under vectors, we learned that direction, it is usually an angle. Theta is equal to tan inverse of y component over x component. So this is the formula for the direction. So we're going to say tan inverse. So for this one, now you don't have to stress too much, you just pick what is available. So for this one, the y component, which vector is going in the y-axis? It is this one, 10. So we say 10, it is the y component, it is the one going in the y-axis. So 10 over the x component, it is 5. Yeah, so 10 over 5, that is 0.5, and then tan inverse of, that is 2. Tan inverse of 2, you get 26.5. Yeah, so you just punch this in the calculator. So this is the direction. Yeah, so if there are no questions, I'm going to give you a homework. So this homework, you can just think about how you can solve, and then you can even submit if you want. Okay, go ahead. Okay.
After theta to the 6.5 there, the angle I calculated, either the angle from 90 degrees rather than to the 80 degrees. So I think I'm going to substitute from 90 or just leave it like that.
Oh. Okay, so you're asking now, aren't we supposed to subtract from 90?
Yes, or like that.
Oh, okay, so that's a very good question. So under vectors, we learned that I explained very much that when you find the theta using this formula, Ry over Rx. So for those who, maybe if you are just watching this video, you can check out the other video on vectors, and there's also a document. So when you calculate theta using this formula, you should always know that the angle which you get, it is between the resultant, which is R, and the x component. Yeah, so I hope you remember this. Always when you calculate the theta using this formula, the answer which you get is between the resultant vector and Rx. So now let us plot the problem. We had something looking like this, and then it was also going due east. So meaning this is our Ry. Ry is simply meaning in the y-axis, and then here this is our Rx. So the resultant vector is here in between. Okay, so this is quite interesting. So this is the resultant vector. So at this point, this value of theta, it is at here between Rx and R. So this is the theta which we have found. Yeah, so, and then for this one, for us not to be so confused, we are going to draw it in standard. Yeah, so at first we are calculating the relative velocity. So let us draw it according to standard, so that we ensure we read things in the y-axis, or in the positive y-axis. This one, Tracy, I'm going to Caterpillar for her. So Tracy, you are welcome. We're about to conclude. How can you be this late? Yeah, so but don't worry, you are going to check out the recorded lesson. So we're done answering this question. I'm just trying to attend to the question which was asked by someone. So remember what I said, due east, it means something is going like that. And then there's no difference if you draw the vector here. This is due east. Yeah, so the resultant vector R is always in between. R is between Ry and Rx. So this is the resultant vector. So remember, when you calculate theta, theta is always between the resultant vector, which is this one, and Rx. So meaning in such a case, theta is here. So in this quadrant, it is being read from the positive x-axis. So we just get the same answer. Yeah, the one which we found, we just get it the way it is. Yeah, so your question was very good. It's very good for analysis. You start thinking about the whole situation so that you get full marks. But under relative velocity, the mega tip I can give you is that you can just get the same answer you will find. It will usually be correct. So now we're done with this question. I was about to give you a homework. So this homework is, let's say we have a car. So you should screenshot, or you can even write it down as you are following the lesson. Write it down in your book. So I'm not going to write the full. Is that a question? Like, there's no question. Yeah, so don't feel shy. You can ask. If you ask me on WhatsApp during the lesson, I'll be able to respond afterwards. So this is the homework. We have a car which is moving due west. A car is moving due west at 20 meters per second. And then we're trying to okay, so this is just vectors. If it is moving due west, yeah, I'll just look for actual questions. I don't want to confuse you at this point. So now ensure you understand this question. You can solve it over and over again. Yeah, and then we still have more examples. If you are tired, you can let me know. You go for a break, you'll find us. So a passenger walks with a velocity of 1 meters per second along the air saw of a train. And then for the screen, I know sometimes it is not showing. Yeah, so all this is just network. So we just try to survive. So a car or a passenger is walking with a velocity of blah blah blah. So we have a train. So for Tracy who just joined us, we are going to understand this. I know you found us when we were concluding the previous example, so you feel lost, but you are not behind. You are just in time for this question. So we have a train like that, and then we have what can we say? We have Maureen. I hope Maureen will not feel upset. She's also in the lesson. So we have Maureen is moving at a speed of 1 meters per second. Oh, it's 1 meter per second. The train is moving forward with a velocity of 3 meters per second. And then Camorin is also moving in the train, but she's moving at 1 meters per second. Okay, so this is the situation which we have. So what is Maureen's velocity according to a fellow passenger on the train? So if we have another passenger who is seated in the train, and then this passenger is looking at Maureen moving, what is the velocity at which the other passenger is observing? Yeah, so just hold on. I plug in my phone. It's battery low. Yeah, so just hold on. Give me a minute. Okay, we proceed. Tracy, welcome back again. Oh, thank you for joining. So we have someone who is seated and then someone is walking. What is the velocity? So here we're simply saying what is the velocity. So we're going to say, okay, this one is A, and then this one is Maureen, M. So what is the velocity of Maureen? We say the velocity of A to M. Yeah, I'm getting confused here. So the velocity of, if we say the velocity of A with respect to M, it means that the velocity of A looking at M, like that. So, but that's not my question. So the question here is, what is the velocity of Maureen M when she's been observed by person A? So this will be equal to, so in the first example, it was a very simple question, everyone managed to answer. If Maureen is just seated, the velocity will be 0 because she's sitting. The velocity will just be 0. Okay, but since now Maureen is moving, then her velocity is 1 meter per second. So person A is observing Maureen to be moving at 1 meter per second because they are both in a train. So this person, she won't be feeling like Maureen is moving very fast because she's also on the train. Yeah, so and then you are going to understand it better. Coming to question B, what is the velocity of Maureen being observed by someone who is outside on the earth? So we have Tracy, she was left for the bus. Sorry Tracy, I'm troubling you. So I have Tracy who was left on the bus. It's the train, it is moving. So when Tracy was observing all this, the simplest explanation I always give is, Tracy is observing two velocities. She's observing the velocity of the train. She's also observing the velocity of Maureen. So we just add the two velocities. So it says velocity of the train plus velocity of Maureen is 1, or more, the train is 3 meters per second. So the train is moving forward and then Maureen is also moving forward. So meaning the person is observing two velocities. So 3 meters per second plus Maureen's own velocity. So the final answer is 4 meters per second. Yeah, so this person, she'll feel like Maureen is moving very fast because the train is speeding and also Maureen is walking. So Maureen will disappear very soon. Yeah. So if there are any questions, you can unmute and then you feel free to go ahead. Seems like there are no questions. Okay, so that's how you answer this. Do I have more examples? Okay, we have this one which is scary from I don't know if it's the tutorial sheet. Yeah, so I said in the group before the lesson that you can even send a question which would want us to go through. Yeah, so we might not be able to solve everything. For some other questions, I might just make some videos. Is that a question from who is that one who has unmute? Yeah, so but whenever you have a question, you can always ask. So I was saying this will be our last example. Yeah, for some other problems, I remember there's a very good question on relative velocity in 2 dimensions. I'm going to make just a short video on that one alone. Just answering one question. Relative velocity in 2D. So this is one dimension. We just look at one thing, the other thing, then the same plane. So to conclude, let's say I know you don't have cars, but just imagine you drive due north. So due north meaning you are going straight. So imagine you drive due north on a road at a speed of 88 kilometers per hour, and then a truck in the other lane is approaching you at a constant speed of 104 kilometers per hour. So find the truck's velocity relative to you, okay, and your velocity relative to the truck. And how do the relative velocities change when the two cars pass each other? So I got that this question is coming from Mr. Hey. So just hold on. Oh, network problems. Yeah, so before we were disrupted by network, we are looking at this situation. So you are driving due north, a car is coming this direction, and then they are asking you what is the relative velocity, what is your relative velocity to the truck, and what is the relative velocity of the truck to you. Yeah, so let me just admit someone into the lesson. Yeah, I hope the screen is visible. So I just want to admit someone who's requesting to join. Okay, so we quickly finish it up. So to answer question A, the truck's relative velocity to you. So here in physics, we have what is called the coordinate system. We have the polar coordinate, the Cartesian coordinate system, all those weird stuff. So on the Cartesian coordinate system, if something is going to the right, in motion in one dimension, in the document I explained, when something is going to the right, it means it's positive. If it is going to the left, we usually put it as a negative. And then for the y-axis, when something is going in the positive y-axis, we give it positive. And then if it is going down, we give it a negative. Yeah, so this is some knowledge which we can use to answer the question. Network again. Yeah. Okay, so network has won. Yeah, so let's just quickly answer the last part and then we call it a night. So we have been interrupted by network yet again. But to just quickly conclude, here I've told you on the x or y coordinate system, something in the positive y, it is plus, something in the negative y, it is minus. So you are going in the positive y-axis, meaning your velocity will be considered to be positive, and then for the truck we can consider it to be negative. Yeah, so under vectors, that was in motion in one dimension, and also vectors, we already said direction can be three things. Direction can be theta, it can be compass directions, due east, due north, those are directions. Directions can also be positive or negative signs. Yeah. So that was just some recap. So now let's answer the question. They are saying, what is the track's velocity? So the velocity of the track relative to u. So we just add the velocities. So here, this is a very fast scenario. So for physics, when you understand it beautifully, you'll be able to imagine things. So like you can see the earth. You know what? If you have someone standing on the earth and they are looking at the train, okay, so I'm going to explain this after solving. So the track's velocity relative to u, we're going to add. So the velocity of the track, since it's going in the negative y, it is coming down. So they gave us it is 104, and then its direction is negative, meaning, its direction is negative. So negative 104, that is the track's velocity. And then we say plus, we add 88, plus 88. Yeah, so the only thing here is we are able to understand it very nicely if we say we have a track. If it is coming down like this, let's say the velocity is 10 meters per second, and then another car is going in the same direction. Now if we say maybe it's 5 meters per second, the relative velocity we can add, they are going in the same direction. But now in this case, since they are going in the opposite direction, this car, you are going in the opposite, meaning we put a minus. Yeah, so if it was going in the same direction, it's just going to remain a plus. So when you add, you remain with 192 kilometers per hour. And then I wanted to explain on this one. So for a person who is just on the ground on earth, when they are looking at the train or when they are looking at the track, the relative velocity for this person, it will just be negative 104. Yeah, so the velocity is just 104, but since it is going in the negative y-axis, you can just put negative 104. So you might wonder, so there's a difference. So this person is here, the other person is in the car, so their relative velocities are different. Since the car is moving, the relative velocity is also having a higher magnitude, 192. But this one, since this person is just standing, then the relative velocity will just be 104. And then on B, what is your relative velocity to the track? So what is your velocity? So your velocity when you're looking at the track. So here we just say yours is 88, and then we say plus, although it won't really be plus because since we're going in the opposite direction, now we put a minus. So 88 minus the velocity for the track. So the velocity for the track, we said it's negative 104. So here maybe you might be confused with the signs, so just understand it from the previous example, which is this one here. So we just say for you your velocity was 88, but since you are going in the opposite direction, you can put a minus. So on this example, what we did, so for this one 104, it will just always be negative in this scenario because it is going in the negative y. So under here it is negative because it is in the negative y-axis. And then for this other negative, which is here, we're subtracting because it is the track is moving in the opposite direction, the same way it was here. Yeah, so If you still feel confused, you can always screenshot a certain part, like I'm not understanding. So negative and negative is positive, and we have 104. When you add, you get positive 192. So that is your relative velocity with respect to the train. Yeah, so that's how you go about relative velocity. So like I said, it will just take practice. It will take you practicing. Yeah. So we'll even do some more examples. Just don't forget to subscribe so that when a new video is uploaded, you'll be very much aware. Yeah, so this is where we'll end with our lesson, and then in the next lesson we're going to look at other interesting things. Yeah, so we end here. Have fun studying.